Good evening, everyone. Maybe we will get started. Let the others join. So, do you have any doubts in previous class lectures and assignment problems? Does anyone have any doubts in that? We have a couple of students here. Yeah, about seven, six, seven of them. So, do you have any doubts in previous weeks' lectures and assignment problems? Since in even our discussion hours, if you have any doubts, you can ask me now. Maybe I will spend 1 or 2 minutes on that. All right. So, does anyone have any doubts? Anyway, you can stop me at any time and you can ask your doubts. Maybe I will start today's sessions and I will try to solve few problems. Okay. So again, today what we are going to do, if you remember, we did was to find the uh, so what we did last week. So if I correctly, we were actually trying to find area ratios, expansion ratio of nozzle. So for a given thrust, how do I design the nozzle? That was the first question we were thinking. So similarly, to today is we will also do some performance analysis on the nozzle. So in fact, we did most of it in the last discussion, but today again we will do the a few more additional parameters which comes into play because in this week, if you look at it, we were looking at let's say the performance of nozzles, like if there is a based on the divergent angles, there's going to be divergent loss, and the thrust is getting affected, and separations, and then the play of thrust coefficients and C star efficiencies. Uh, these things, how does it affect we solve? So based on that, we will solve this problem. So I have only one problem. So I hope this itself will take our 2 hours. Anyway, we will try to finish it before that, so that if you have any doubts, you can ask me. If you want, if you have some other doubts regarding the previous year assignments, also you can ask me. So that's why I made it a little this time. So what we do is we will solve these questions. So and these are the questions which you will be facing in your week 5 assignment also. So that is the reason I made a question based on this. So if you have any doubts, you can stop me anytime and you can ask me. So this is supposed to be interactive, so you can. Having said that, what we will do solving this problem. We have one problem in our hand. Uh, just read out the question. So the question is like, there is a fuel called synthetic fuel called synthin, okay, and this is the fuel developed by USSR. Basically, back then it was USSR. Right now it has been anyway. USSR in the early 1960s they uh, stage, are you uploading this video at YouTube? So all the videos will be recorded and it will be uploaded. So you no need to worry about that. But it if you clear your doubts, that is reason for this. But nevertheless, if you somehow miss it, so we will be uploading in the YouTube. So I guess you have the links of all the YouTube material. So do you have Goka Chandu?
Yes, sir.
So this also will be uploaded after this session. So, okay, you no need to worry about that. Anyway, so what we are going to do is this is the synthetic fuel which has been used in 1960s in their rockets between 1970 and 1980. So just for your information, so that is not going to help in solving the problem. Anyway, the propellant mixture consists of synthetic kerosene as a fuel. So it's going to have a kerosene as a fuel, liquid oxygen as a oxidizer. Okay, and properties of exhaust gas has been given, which is 1.24. Molecular weight is it's also 23.3 is given. So these are exhaust gas molecular weights and specific heat ratio. The propellant mass flow rate is given 400 grams per second. In previous problems, if you look at it, we were asked to find the propellant mass flow rate, but here it's given. Okay, no need to worry about it. And the combustion chamber pressure and temperature is given. Okay, so till now if you look at it, all the questions we have solved is going to have both combustion chamber pressure and combustion chamber temperature. So we haven't studied what happened inside the combustion chamber, which you will be studying from week 5, week 6, and going forward throughout the course. So um, if you look at the, let's say, week 5 questions in week size lectures, there will be there was one lecture which tells about choice of chemical propellants, right? So from there you will start understanding how this chamber pressure and chamber temperature is building up in the rocket. So right now we no need to worry about it. Question in chat box. So it says, sir, in the assignment of week 4 solution, there was a mistake in first and second question. All right. So Akash B, are you here?
Yes, sir.
So what was the question? Maybe we will quickly review it and come back to it. Assignment
The
4,
question
right?
was to find. Yes, sir. So the question was to find an escape, jet velocity of the following rocket, and yeah, the solution there it has already considered like the molecular mass was 4 gram per somewhere like 4 grams, and in question is directly taken as 4. It should be 4 into 10 raised to minus 3, right? Sir?
So molecular problem, we can just quickly look at it. So molecular weight given was 4 gram per mole, is it?
Yes, sir.
So basically, if you want to convert it, then it should be 4 into 10 power minus 3 kg per mole. And then this is how you need to
Sir,
implement. Yeah.
sir, molecular weight is just 4 gram. No, there is no gram per mole.
How come molecular weight should be given with
Okay,
gram
okay,
per
okay,
mole?
okay. Sorry, sir. My mistake. My mistake.
Yeah, no problem. So actually, I'm looking at the assignment 4 right now. Your doubt? Hello?
So the gram per mole should be written in 10 raised to minus 3, but it's written only as 4.
Yes, so gram per mole should be written in 10 power minus 3. I do not understand. So this is how you should substitute. Okay. So this is the correct way to substitute in the relation. Is this how you substituted?
Yes, sir. The answer they got and answer I got was different entirely.
Solve that here if you are okay.
Okay, sir. Yes, sir.
Pressure of helium gas to be 300 Kelvin. Okay. And pressure ratio on expansion. Okay. So pressure ratio on expansion. So it's
4,
going
sir.
to be PE.
Yes, sir.
So we need to find jet velocity, right?
Yes, sir.
Okay. What is the relation for this jet velocity relation? Do you remember?
Yes, sir. Root of root of what's it? It's something like root of Tc into gamma by gamma minus 1 into molecular mass into 1 minus Pe by Pc raised to gamma minus 1 by gamma.
Wait, let me look at the formula myself. Quite a big formula. We can also derive it, but I do not want here. Okay. Is this something like this? 2 comma y comma minus E by TC.
Yes, sir. Yes, sir. Yes, sir.
So if we substitute 1.67 divided, this R is going to be R naught by molecular weight, right?
Yes, sir.
This 8.314 joule per mole Kelvin, and molecular weight is going to be 4 into 10 power minus 3 kg per mole. So you will end up getting
So in our uh, so in our question, our number is given as like 8,340. Like
given in question.
8,340.
Okay, 8314 joule per mole Kelvin, 3 kg per mole.
Hello. Hello, sir. Actually, it is 8.314 only.
Yeah,
That is misprinted actually.
that's what I'm also thinking. So, is that the reason, Akash, you are getting wrong results?
Oh, I think so, sir. Yeah.
What is the R you are getting? Did you calculate like this?
No, sir. I just directly put 8,314 by. Since the
So,
question it was given like R naught is equal to that value. Yeah.
that turns out to be very large. So, yeah, substitute 8314, then it turns out to be very large. You have to substitute 8.314. Sure why the question says 8314.
Oh, okay, sir.
So, I think there is a printing mistake. Maybe what I would suggest is if this is the problem, if this is the problem you have, suggest is you write a, I mean, you can write email, no? So you can write in the discussion forum telling that question is misprinted. So have you wrote it before?
Uh, no, sir. Like I was want to verify whether it's correct or not. So,
Is the what is solution says that we have solutions also, right?
yes, sir. It's something like 11125, like something.
Question has a problem. Yeah. So the computer in terms of 831. No, I mean, they substituted it as uh, joule per mole Kelvin. Okay. Yeah, yeah, yeah. So I think there is a printing mistake with R naught. They have calculated it as solution. What I see is a division by 4. I'm not seeing a division by 4 into 10 power minus 3, which means they took the 10 power minus 3 above and they multiplied to get 8314. It doesn't mean they took R naught to be 831. There is a
Okay.
there is a printing mistake with the question. Uh, Maybe what you can do is you can mail them or you can post it in the discussion forum, and you can tell there is a mistake in the question. It says 8314. Is this happening for other assignments too? Let me check.
No, so this was the first I guess.
See this week 5. Yeah, week 5 it has been corrected. If you look at it, R naught is 8.314. So in week 4 there is a printing mistake. So you write an email or you put it in the post it in the forum, and let's see what they reply. Okay. So do you have any doubts regarding the concepts, or is this the problem?
Sir, I have another doubt regarding the question, sir. Can you just wait for a minute? I want to just take a look at the question. Like,
You share? I didn't get.
yeah. So in the week 4 question, like I have questions regarding Mach number and all. So I just want to like look at the question, like it was a true or false question. I can't remember it.
Okay. So which question is the? So you want me to share, or
Yeah, it would be. I think it would be great, sir, if
so
you just
which
share it.
week?
So
Which
everyone
week?
can.
Which week is it?
Week 4 itself, sir. Week 4.
Okay. And see my screen. Were you able to see my screen?
Yes, sir. Yes, sir.
Yeah, I have this week 4. So which question is that?
Sir, it was a true or false question.
Okay, true or false question.
Yes, sir. It was regarding something about Mach number. Sir, like throat is less
Is
than
that?
when shock. Yes, sir. Yes, sir. If the Mach number of the nozzle throat is less than 1, shock waves are formed in divergent section leading to loss in tone. It is true, right, sir?
So if the Mach number shock waves are formed in the Mach number nozzle throat
And
is less than 1, shock waves are formed in the divergent section leading to loss in the throat. No, actually it's false. See, the Mach number at the nozzle throat is
okay.
less than 1. So, okay, let me try to clarify it. So, okay, so this is a CD nozzle, let's say. Okay. Um, cannot see it, right?
Yes, sir.
Is this the question you have a problem?
Yes, sir.
Impact screen, right?
Yes, sir.
Okay. So now
Yeah.
we have this CD nozzle. So we know is to have a choked flow, we need mass flow rate at the throat to be 1, right?
Yes, sir.
So if the Mach number is less than 1 at the throat, okay, so we do not have a choke flow. If we do not have the choke flow, let's say if I let me draw it here. So throat, okay. Let's say if I plot the Mach number, okay, so it 0 exactly, but just 1. From lower value and it reaches 1, and if it's a supersonic flow, it's going to be go like this, okay. So this is at the exit. So this is the fully isentropic supersonic flow, which is ideal case. It happens only at the desired altitude for which the nozzle has been designed. But let's say you haven't reached the uh, Mach number equal to 1 at the throat, uh, is it's going to reduce. It's not going to reach supersonic. So only when there is a supersonic you will have shocks. So let me explain you in a different way. So what do we know about? We have a relation, right? So what do we? I exactly don't know the relation. It's like dA by A is equal to, I believe,
dA by
one.
dA is equal to uh, 1 minus like m square by dA, that's right.
Uh-huh, that one.
Minus dA by dA 1 by 1 minus m square.
So is this right? Whatever I wrote, dV
Sir,
by.
note that it's dv by v equals to minus dA by a into 1 by 1 minus m square.
All right. So this is the thing we derive, right? So if you look at it,
Yes.
you can know. So if you look at, let's say Mach number is you haven't reached Mach number equal to 1. Okay, Mach number is less than 1. For example, Mach is less than 1. Okay, everywhere. So let's focus on the convergent portion. Mach is less than 1. Is less than 1. At the convergent portion, what happens? dA, the change in area is going to be less than 0, right? Because it's converging, right?
Yes,
So
sir.
if it is less than 0 and Mach number is less than 1, so this is going to be negative, which means dV is going to be, how will dV vary?
Sir, there should be a negative there.
Where it should be negative?
dA.
So yeah.
Here?
Yes, correct.
Alright, so yeah. So what happens if dA is less than 0? What happens is this term will be, maybe I will write it in a page. dV by V is equal to 1 by 1 minus m square dA by A, right? So in convergent portion, what we know, dA is going to be less than 0 because areas keep on reducing, right? So A2 minus A1, if you do, it's going to be less than 0. So is this clear? Is this clear?
Yes, sir.
Clear. So if
Yes, sir. Yes.
if Mach number is less than 1, let's say, what happens? Minus 1 by 1 minus m square. This 1 minus m square is going to remain positive because m is always less than 1. So it can be 0.5, but 1 minus m square is going to be positive. So this whole term is going to be uh, this whole term is going to be positive, greater than 0, and this term is going to be negative, which is less than 0. So uh, our this is going to be negative, so this whole term is going to be positive, right? So this is negative, negative into into minus is positive, right? So this whole term is going to be positive, which means dV by V is going to be positive, okay? Which means dV is going to be greater than 0, okay? If dV is greater than 0, then velocity is increasing. Now so this is clear, I hope this is clear. So now uh, inside the convergence session, Mach number hasn't reached 1. So what happens then? It's still a subsonic flow. We have this convergent portion. Now we have a divergent portion, okay? Here it is subsonic, which is Mach less than 1, okay? So Mach is still less than 1. Now let's do the same thing for divergent portion, okay? Now Mach is less than 1 because Mach number equal to 1 haven't reached there, okay? So Mach is less than 1. Now dA, what is dA? dA is positive, right? Because in divergent portion area is increasing, area dA is positive, which means Mach is still less than 1. So what happens? dV by V is going to be minus 1 times this positive quantity will be there. So this will make it to be negative, right? So which give rise to dV which is less than 0, which means velocity will decrease. So if you haven't reached, so velocity decrease means Mach number again decreases, it's going to be still subsonic. So if you come back to this plot, the Mach number is going to, sorry, so the Mach number is going to rise like this, and then since it hasn't reached the Mach number equal to 1, it falls down again. Okay, so which means if subsonic flow is something like the speed of flow is actually less than the speed of sound. So if you look at the the pressure perturbations moves with the speed of sound. So what is sound? Sound is nothing but pressure waves, right? So if you look at the pressure waves, it is going to move with the speed of sound, and because of that, in a subsonic flow, the you will know all the information surrounded by you. Okay, because if there is some change in pressure, you will be able to feel it. So reach you faster because you are moving at lower velocity. Okay, so that is the reason if I have a subsonic flow, the based on the pressure gradient I will be having a my velocity will keep decreasing, and it will become fully subsonic. So there is no shock. When the shock happens, when the information is not able to reach on the downstream. Okay, so if I'm moving with, or from the downstream you are not able to get the information. So if I'm moving with more than pressure, waves can travel only at the speed of sound, then what happens? I do not have any knowledge stream, right? So that is the reason when it goes, but downstream I have a let's say, let me write it down. Let's say if I reach Mach 1, okay, and this is some exit pressure which I designed it. So but my pressure is uh, let's say less than the exit pressure. Okay, so our exit pressure. So if we plot the, where do I plot it? Let me tell you when does when does shock forms. Okay, so
Okay, sir.
this is throat, right? Or yeah, and here it is exit. So let us consider this thought experiment. Okay, so I have a big the tank. Okay, and I have a small orifice through which fluid can fluid liquid or gas, anything. Okay, this can go out. Okay, uh, initially my
Yes,
tank
sir.
is at high pressure. Okay, let's say I have a, this is tank, okay, which is at 1 megapascal. Okay, and this is ambient pressure which is also at 1 megapascal. Now you see what happens, both the pressures are at 1 megapascal. So what happens, there is no pressure gradient stay in the tank, right? So is that clear? So in order to have a flow inside this nozzle, you need to have a pressure gradient. If there is no pressure gradient, the flow is not going to happen. Now, so this concept is clear, right? So without pressure gradient, flow cannot happen.
Yes, sir. Yes, sir.
Now, what you do is you have this ambient pressure. You try to reduce it. Okay. Now let's say you reduce it, let's say to zero point 0.5 megapascal. Now you have established a pressure gradient because inside the tank I have 1 megapascal, and outside the tank I have zero point 0.5 megapascal, and there is an orifice or a place through which a fluid can flow. So what happens? The fluid flow takes place, right? So, so since it's a converging nozzle, and let's assume it's a low speed flow, or Mach number is less than 1. What happens? So it's going to be increase, right? Because it's in the converging portion, the subsonic, if the Mach number is less, in the divergent portion, what happens? It's going to decrease. That's what we saw, right? So based on this,
Yes.
this relation is going to do that. So here there is no shock formation, because as soon as I started, so initially if you look at the profile at t equal to 0, it's going to be like this. Okay.
So,
Yeah.
hello. So, like, what causes this shock waves? Like, what are the?
Yeah. So
Is
that
it
is the
because of
concept.
under?
Haha, that is the concept I'm trying to explain. So that's why I took this thought experiment. Understand that. So this is at p equal to p naught, which is at 1 megapascal. Okay. Now I establish the pressure gradient. What happens? It's going to be rise. It will rise like this. Okay. Then I have to. Wait a second. Scale here. This is p is equal to 1 megapascal. So initially I am in this state, okay, and then I reduce the exit pressure to 0.5 megapascal. Let me 8 megapascal. Okay, so my exit pressure is 0.8 megapascal. Okay, now what you know about it? The how does a fluid know that the exit pressure has reduced? Because the pressure wave is going to travel from the downstream to the upstream, right? Then only fluid knows, okay, there is a pressure gradient, I have to flow out. Okay, so I have reduced it. So this is the first thing I'm doing. So what happens? Okay, there is a pressure gradient and I need to flow. So what it does is it reduces. So it reduces like this, and then it's going to be, it is going to go like this. Here it is pressure, it's not velocity, please note that. So let's say if I want to plot the velocity also for this thought experiment, let me plot it here. So initially I haven't established any velocity. Okay, p is equal to 1 megapascal, and now I have established a velocity, because the fluid knows that there is a pressure gradient. Okay, so I will increase till some velocity. So at the throat it's going to be maximum, because at the conversion portion we know the velocity is going to decrease. Okay, so and then it will reach to some, it goes out with some velocity, and the pressure here is going to be 0.8 megapascal. Remember, this is a velocity plot. Okay, this is the
Sir,
pressure plot.
sir,
Yeah,
hello. Sir, that means it is important to design a nozzle to achieve choked flow.
exactly. So here the mass flow rate is going to start increasing. Okay, that is what we saw in another plot, where we saw that there is something like this, and after the choked flow, here is where the mass flow rate is going to be maximum. This is the corresponding point where the choke flow happens, and after that if you increase the pressure gradient, it's not going to uh, PE by PC, or if you increase the pressure gradient, it's not going to increase the mass flow rate. So please bear with me, I will complete it. So here I'm right now induced a small pressure gradient, which has made which has made some flow to happen, right? So, and we know how the flow happens, because if the in the convergent portion subsonic flow is going to increase it, and the divergent portion is going to decrease. So let me reduce it to some another pressure. We call it PC, or we call it PCR. Okay, I will tell you what is this PCR. At that point, what happens is, we will see in let's say this can be velocity or Mach number based on the thing. So it can go and reach some point where it is Mach number equal to 1. Okay, and then it reduces and goes up. So this pressure is something called critical pressure. Okay, so for this, okay, this pressure, this is the uh, pressure gradient you need to establish Mach number 1 at the throat. I have a higher pressure here, I have lower pressure here, and keep on reducing. And at one point, what happens? The flow is, if you keep on reducing, then there is a big pressure gradient, so flow is going to get accelerated, right? So at one point, what happened? It has accelerated to the throat, and it has reached Mach 1. Once you reach Mach 1, this is where the problem reaches. The same equation what we saw here is going to behave differently. In the convergent portion, the velocity is going to reduce, and in the divergent increase. Okay, so let me move on with this thought experiment. Let's say I have reduced it even smaller. Okay, let's say PZR minus zero point 0.1 megapascal. Okay, so now what happens? You need to think, I have reached Mach 1. Okay, so once I reach Mach 1, I'm not going to know what happened, what in the downstream, right? So I will keep moving, and then what happens at some point of time? Oh, I have to reach the ambient pressure at the outside, because that is what the ambient pressure, right? So what it will do is, so suddenly I need to reduce it, and suddenly it puts a shock wave here. It's a shock wave here, and it's going to reduce, and it becomes subsonic, and then it reaches the think of it like this. So I don't know the downstream, so if I don't know the downstream, I will be accelerating and coming, and but my pressure at the downstream should be low, it will be low, because I am accelerating, and I do not know what is the back pressure. So if I am in that stage, what has to do is, it has to suddenly reduce all the pressure to reach the back pressure, right? This sudden discontinuity, or this sudden variation of pressure, is what we call shock wave. So it puts a shock wave such that it increases its pressure and reach the ambient pressure. Okay. So in the Mach number plot, if you look at it, it is going to be Mach 1, and it's going to be after that, it's not going to increase here, and it's going to be to suddenly decrease, then it has to reach this pressure, and this is called shock. I drawn wrong here. Going to be Mach 1, going to increase. Once Mach number 1 is reached at the throat, the flow dynamics inside the convergent portion is not going to change, because after that, we don't know what happened in the downstream, so there is no way we can get information from the downstream. So even if you keep reducing the ambient pressure, once Mach number is reached at the throat, from the so how do we know pressure gradient has established? From downstream, the pressure information has to reach the tank, right? Then only fluid can accelerate. Okay, there is a pressure gradient, I will accelerate more, right? But if I reach the Mach number 1 here, I am also moving with the equivalent to sound velocity, so there is no way I can get the information to the upstream. So my convergent portion part is going to get fixed, it's not going to change at all thereafter, once I reach Mach number 1 at the throat. Then enough pressure gradient to fully have a isentropic flow also. So I will keep accelerating, but suddenly my pressure is very high at the back. So what I have to do is, I have to decelerate suddenly, right? So this is Mach number greater than 1 is like very high velocity, and I need to suddenly decelerate. So what it has to do is, it does a shock wave. So that's where shock wave comes. Shock wave, what happens in shock wave is sudden change in properties, or a discontinuity in the pressure. So suddenly at the upstream of shock wave is going to be very high in very low pressure, and the downstream is going to have very low velocity with very high pressure. So this is the reason it puts a shock. So you can think it like if there is no supersonic flow, there is you cannot form a shock, right? Because you know the information beforehand, and so though there is no need to put a shock. But if you don't know the information, then it has to put a shock and it has to reach the ambient back pressure condition. Okay, so that is the reason it forms a shock there. Is that clear, or did I confuse more?
So like I'm confused with like shock diamonds. Is the same reason for the like
Yeah, so
like
okay, let's carry on this thought. Okay, uh, let me redraw it a little bit smaller so that till now it is clear, right? So once it happens,
yes sir.
so if you keep, let's say you keep reducing this pressure, okay, so now PCR is zero point 0.1 megapascal. Now you reduce it to there's 1 megapascal side. Let's reduce it to another 2.2 megapascal. Now what happens, this shock, since you have even more accelerated, so this shock is going to be moved like this, and then it's going to shock, and then it's going to reach this. Then finally it keeps on doing it, okay, and then until it finally reaches the uh, isentropic pressure gradient. So why we call isentropic? Because it's going to be isentropic process. There's no heat release, and then it's also going to be reversible. So that's why we call it isentropic. So keep on reducing the pressure, back pressure. So it's going to this shock position. If you look at this shock position, it's going to keep on moving on the moving outside. Okay, at some point of time, it get blown out of the nozzle. So it got blown out of the nozzle, and if it is, yeah, so there will be shock here, okay, at some point of time. At that later, what happens? There will be another shock, and this shock is going to keep on moving out, and at some point of time, what happens is, uh, the, in order for these are called normal shocks. So if you take a compressible flow course, which I strongly recommend if you are interested, uh, you can learn more about these shocks and different kinds of shocks. So these are called normal shocks. It's going to be straight, okay, and what happens is, this normal shock will keep on moving as PC by PE increases, which is PC is nothing but tank pressure and PE is nothing but back. Okay? If as you keep on increasing, or in some other sense, you keep on decreasing the back pressure, the shock is going to keep on moving, and at some point of time, what happens? There will be some back pressure for which it cannot put really a shock. So what happens? It puts an oblique shock like this. Okay, so oblique shocks requires a less pressure gradient than the normal shock. In normal shock there is going to be very high pressure gradient. So as you keep on reducing the back pressure, um, what happens is there won't be enough pressure gradient to withstand this normal shock, which becomes oblique shock. Okay, oblique shock means it's a slanted curve. So once it becomes oblique shock, but still PE doesn't match PC, so what happens, it becomes oblique shock so that it reaches, and then what happens, it gets it comes here, and then it gets reflected, and then it forms this expansion waves, right, and then that also gets reflected, and then it normal shock again, and then this is what we call mark diamond, right. So these diamonds happen as this normal shock get out, like if your pressure gradient is not able to withstand normal shock, it puts an oblique shock. Once oblique shock has formed, because of the conservation of masses at the nozzle end, it just the waves just reflect within that domain. So once it gets reflected, due to, so if you are interested in more details, uh, okay, so now so now we know that there is, let's say we have reduced it so much, okay, so this is where fully expanded, right. So we have reduced it so much, and then let's say this is little above, okay, here, but this pressure gradient is not enough for a normal shock. What happens is it puts an oblique shock. It should put a oblique shock because it has to reach the back pressure. So here P, let's call this back pressure or ambient pressure. Okay, so let's call it back pressure, and the exit pressure may be at the inside the okay. So let's say PE here it is greater than no sorry back, right? If it is less than only, then only we have to reach the back pressure. So we will put a shock such that shock, what happens, shock what does is it increases the pressure, right? So always shock what does is it increases the pressure and reduces the velocity. So and expansion wave, what it does, expansion wave, it does it reduces the pressure and increases the velocity. That is the difference between shock and expansion wave. So we need to meet the back pressure. So what we will do is we will put a shock wave there. Okay, we will, in the sense the fluid puts a shock wave there. When you put a shock wave, what happens, this P exit is going to be equal to P back, but you see the flow has changed, right? So now since you put a shock wave, the flow is going to be going like this. This is the central line, right? So this is the nozzle. We cannot withstand a normal shock. Normal shock requires very high pressure gradient across the shock. We have low pressure gradient, so we put a oblique shock, and then so that oblique shock it does balances the pressure. So basically, you have balanced the pressure. But what happens? Diverging from the midpoint. So you need to conserve the mass. So this is one of the reason. What it does is it puts another shock wave. So how does it put another? This is called reflection of this shock wave. Okay. So it puts another shock wave so that it comes in, and what we know about shock is it's going to increase the pressure, right? It is more. One second. Little bit of expansion here. One second. But this it has what is the other so this is in the shock where the Mach number is going to decrease, right? Here is going to be lesser than what it has exited. So central section P is less than P infinity, and then it again puts a shock wave. Right, I was right. Okay. So this gets reflected. Okay. Basically, if you want to draw a line, you can. So here, give me a minute. Okay. So yeah, let's forget this also. Yeah. So now we know PE is less than PP. So but it cannot withstand normal shock. So I will oblique shock. Okay. So now what happens? Since I put an oblique shock, the flow is going to be so reason to put an oblique shock is to match the back pressure, right? So my PE becomes PB here. Now what happens? But the flow is going to go towards the central line, right? So it is going like this, and I put a shock wave which turns the flow. So it is going to go towards the central line. So if you keep, if you draw this, but I have to conserve the here because it cannot keep on go into the central line, right? So what it does is it puts on reflective shock wave. That's what we call here like this. Okay, and what it does is it sort of, since this is not clear. So it converges. So what it should do is it has to make the flow to be parallel to the central line. So mass. So that is the uh, from mass conservation. This comes into picture. So what it does is it has to change the direction of the flow. So uh, changes the direction of the flow. That is the reason for this reflective shock wave. But what happens? We know that if there is a shock wave, the pressure is going to decrease, right? So now what happens? The PE, which is the gas pressure, is going to be than PB. So across the shock wave, pressure will increase, velocity will decrease, right? So PE is going to be greater than PB. Now again we have to match the exit pressure. So what it does is it does something called expansion wave. So thing like this. Okay. So in expansion wave, what did I say? Uh, uh, in expansion wave, the PE will the at the downstream pressure will decrease, right? So I have a higher pressure. I will put an expansion wave so that it reaches the back pressure. So it again reaches the back pressure, but what happens again? The flow direction from the central line. Okay, so it diverges from the center. So side boundary layer, if you say, or the shear layer, it's going to now it's going to widen. So in order to again conserve the mass, what it does is it puts on another expansion wave called reflected expansion wave. So what it does is it again makes the flow to be straight, but expansion wave, what it leads to decrease in pressure. Now again PE becomes less than PB. Now if you look at this uh, position and this position, both are actually same. What it does is the fluid has gone through a oblique shock expansion. So that is the reason. And again we came back to the first step. So what it has to do now, this has to repeat, right? So again I have to match the back pressure. What it does is it puts on another shock wave. Upon putting another shock wave, the flow is going to converge and reach the central line. In order to match the mass conservation, it's going to again, there's going to be a reflected shock wave. Okay? And if you see, if you look at this part, this reflection to this expansion, this part is going to be a little bit bright, or maybe this part is going to be a little bit bright, and this is what we call it as shock diamonds or mark. It's in between these two. So these things happens once this normal shock is blown up. and this is where this flow separation, all those things happens within the even with the normal shock there is a possibility. This is the uh, shock diamonds concept. Like, is that clear?
Yes, sir.
Yeah. So basically, you can take a compressible flow course, or you can read a book by John Anderson, Compressible Flow. Uh, Basically, what it does is you need to match the pressure, and you information doesn't reach you. So what you do is you put a shock wave. That's all. So you put a shock wave and you increase the pressure so that it will reach the back pressure. Upon doing that, it changes the direction of flow, and so the mass it has to put another reflected shock wave, and which again makes the pressure to be greater than. Again, you need to match uh, the ambient pressure. So this is for PE, which is P exit pressure is less than back pressure, which means it has to put a shock wave to reach the higher pressure. Now, if the exit pressure is greater than back pressure, this is what we call it as what did we call it? Is it the over expanded or under expanded?
Overexpanded, sir.
Yeah, because exit so pressure is lower than the back pressure, which means you expanded more, like expansion in pressure. So you have reduced pressure more in the nozzle, so which means it's a over. This is over expanded nozzle. Now you keep on. Now if you, let's say all these process happens in our thought experiment also, and then you will keep on reducing and you reach this isentropic pressure where this all these shock diamonds will be flow going on. Okay, so but that pressure is, or it's very sensible to that, so you will always have a shock time. So now let's say you reduce this pressure even below. Okay, now instead of reaching this pressure I have reduced it even below till the x-axis. Okay, then what happens, which means that P exit is actually greater than P back. So exit pressure is the gas pressure which it reaches the exit of the nozzle, which is greater than back pressure. So because I have reduced it even more, that time what happens, the same thing is going to happen in the CD nozzle, but this time we have P exit greater than P back, right? So this time we do not have P exit is greater, so we need uh, reduce our pressure somehow, right? So what it will do is it will put a shock wave first, sorry, expansion wave first. What it does is it's again it's going to diverge the flow. So basically you will be, this is P exit is greater than PB, right? So you will be at this stage. Okay, and then you will see a expansion wave, and then there's going to be a wave, and then the pressure is going to be high, so it puts an oblique shock. So then again it's going to be pressure is going to be low, so an expansion wave, and this keeps on going until it dies. Okay, so so the reason to form a shock is to reach the downstream condition in a supersonic flow, simply if you want to state it. Okay, so if there is no supersonic flow, you always know what is the downstream condition, so you know, because you can adjust it throughout. So that is the reason you cannot have shock when the Mach number is less than 1 at the throat. Is that clear?
Yes, sir.
So if you have any doubts, you can still ask me. I'm not sure whether did I confuse you or I gave you the.
So, like, I have another question. Like, uh, sir told sir in the lecture told, like, in the core booster thrusters, you don't need a divergent nozzle. Like, what was the reason for it? I can't really understand.
In the in the
Cold boost thrusters. You don't need a divergent part of the nozzle.
So maybe because you no need very high pressure. So sorry, maybe because we no need very high velocities. Because but basic understanding lies there. Like if you have decrease, if you have supersonic flow in convergent decrease and divergent portion, the velocity is going to increase. Okay, that is the basic thing you need to understand. The other thing is the I don't know about cold boosters, but there it can be due to maybe you don't need a very high um, velocity at the exit. So they will just converge it and they will put they will maybe they may not even reach Mach 1 at the throw. They may not require that or something like this. So is that what you're doing?
Yes, sir. He was talking about Mach numbers. Like, yeah, that was a question he told. Like cold boost thrusters. We don't need a divergent path. We can just kept it till the throw.
Maybe I will go through the lecture and I will get lecture is that week three or
Uh, so,
should be week four, I guess.
yes, sir. He was talking about Mach numbers. Like,
Okay, okay. Just talking about morning. Okay, I will look into it and get back to you.
okay, sir.
Session. But basically, this is the underlying concept you need to understand. You need to keep that
Okay.
in mind. So, to do not reach a subsonic flow, then it is actually no need. You should not put divergent section at the nozzle because if you are going to reduce the velocity after that, and you do not want that. Why do you need that, right? Sometimes even in let's say if you take aircrafts moves at 9 or point 0.8 and the exit velocity you actually no need. It's a little bit different. It's not same as rocket propulsion. You will try to optimize the propulsive efficiency of aircraft. So what you will do, you will try to match the exit velocity of the exit velocity of gases from the gas turbine engine or aircraft engine to be equal to the velocity of the aircraft, which is at Mach point 0.8 or point is subsonic flow at the exit. What you will do is you will not put a divergent portion. You will just put a convergent portion and you will just leave it. So that is the reason you will also see a lot of gas turbine doesn't have divergent portion. Correct. So whenever you do not need a supersonic flow, you do not put if you do not need supersonic flow and your Mach number at the throat is going to be less than 1, it is beneficial to not put a divergent section there because you need if you put a divergent the subsonic flow velocity is going to decrease. So you do not want then that could be the thing professor must have mentioned, but I will look into it and come back to you.
Okay, sir. Thank you.
Any other questions? I think 1 hour is already gone. No problem. So what we do is we will quickly solve it. It's not a very big question. Uh, Let me just write the given. So I think I have already, maybe I will remind you. So we have a rocket which has the is going to have gamma to be 1.4 and the molecular weight of gases is going to be 23.30 kg per kilomole. You need to note the units very carefully. So this time they also gave the propellant masses. Okay, mass of propellant or mass flow rate or the mass burn rate of the propellant or the mass flow rate because mass conservation, right? Mass conservation means mass flow should be same everywhere. Okay. uh, and mass flow rate is given as 400 kg per second. If there is a mass, if 400 is going to be equal to the mass flow rate at the throat, and it is going to be equal to the mass burning rate of the propellant. Okay, both are same, and we also have combustion chamber pressure, which is 36 atmosphere, and 35 or 36, 35 atm, and we have chamber temperature, which is 3670 kelvin. Okay, so now we have all these. So what we have to, and it also important line is nozzle is designed for optimum expansion at sea level condition, right? It is designed for optimum extension at sea level condition. At sea level condition, we know P ambient is going to be 1 atmosphere. Having understood that, what we have to do is we need to find the area and the temperature and pressure at the throat. Okay, so because I saw some questions which is asking the throat areas and temperatures and pressure, so that's why usually people are not much interested in pressure and temperature at the throat, because only you are interested is Mach number at the throat. So let's solve it. Let's see how we can solve. So what we need is, we need to calculate throat area and the throat temperature, and then throat pressure. So how do we calculate it? Do anyone have any idea?
So P by rho is equal to RT.
So P by rho is equal to RT. So you are telling P by rho is going to be R times T at the throat, right? This is the
Yes,
ideal
sir.
gas equation. How is it going to help us in solving? So if you look at it, we don't know P, we don't know T, we don't know rho also.
So PT can be calculated from uh, okay. Yes, sir.
We have given only these conditions. Uh, do is we should start from what we know. What we know is mass flow. Okay? Going to be equal to mass flow rate at the throat or mass flow rate at the exit, right? It's not going to change because we are looking at steady state conditions, and we are going to, the mass cannot uh, so mass at the throat is nothing but rho t at. Uh-huh.
Like we can relate it with like we know the temperature at chamber, right?
Yeah, we know the temperature at chamber. True.
We can relate it with 2 by gamma plus
Exactly.
1 relation, right?
Yeah, that is what we are going to do.
Okay, sir.
That is what we are going to do. So we can find yeah, so if you want to find temperature first, so I thought I will find the area first. Okay, let me go with your thoughts. Let's find temperature first. Et. So what does that equation tell? Combustion chamber
2 by
temperature.
gamma plus 1 into TE. No, TE by TC is equal to 2 by gamma plus 1.
T by Tc is equal to 2 by
Gamma plus 1.
chamber throat is going to be T 2 times Tc gamma plus 1. How much is it coming? Can you guys? So you need to think one thing: will the temperature decrease or increase at the throat? So I have a higher temperature at the chamber. So at the throat, increase or decrease?
Temperature will keep on falling right after the.
Temperature will be keep on falling. So that's what I asked. So if you multiply, so how much are you getting?
3276.7.
3 3
3276
3276.
6.78.
Okay, 3276. So, okay, 3276 Kelvin. I'm just writing a ballpark figure. So The temperature is 3276. So at the chamber temperature is 3670. So it keeps on falling. And if I have supersonic section at the divergence part, it's going to keep. Okay. So this is how you find. Or let me state a more general formula used for this. It's nothing but so combustion chamber temperature, or any, we usually call it total temperature. But since you are not aware, we write it like this. So we will come to that. What is total temperature? This is at any this thing is actually 1 plus gamma min. Okay. So wherever you want uh, given the Mach number, you can find the temperature. Stagnation temperature, you can say stagnation temperature or total temperature. Adiabatically decelerate any flow to a zero, and when you do that, since it's an adiabatic process, the temperature of the increase. So when the velocity becomes zero, the temperature is going to increase. So the it's a measure of how much energy I have within a system, which includes kinetic energy and the thermal energy, right? So it's total temperature. And in that, if I have if my gas has total temperature of this much, if my gas is moving at this much velocity, then what is my a static temperature of the gas, then you can relate it through this. We will see there will be one more, maybe temperature at the exit you may need to know. At the time you can use this relation in order to go on. Here the total temperature was supposed to be the combustion temperature, combustion chamber, because at combustion chamber the velocity is going to be very small, so you can relate the combustion equal to total temperature. Okay, so from here only you can get that. So if you substitute Tc by Tt, which is equal to 1 plus gamma minus 1 by 2 mt square. So Mach number equal to 1 at the throat, we know. So here we will assume it's a choked flow. So Mach number equal to 1. This calculation you will end up getting this relation. That's all. So that is how we get. um, all right, let's move ahead. So we found the temperature. How do we found the how do we find the pressure? So we need to find.
So,
Yes, yes.
so with the same relation like 2 by gamma plus 1 raised to gamma minus 1 by gamma.
Okay, so can you be slow? So PT
Uh,
by PC, is it?
yes, Pt by Pc is equal to 2
Hmm?
by gamma plus 1
2 by gamma plus 1.
raised to gamma minus 1 by gamma. That same isentropic
Yeah,
equation there.
it's actually, yeah, true. So this is nothing but PT by PC is equal to uh, T by TC power gamma minus.
Yes, sir.
Yeah. So basically, I think this should be PC and this should be PT. Or is it gamma by gamma minus 1, or is it gamma minus 1 by gamma?
So one minute, let me verify it, okay?
Yeah, so you can calculate it and you know that pressure is going to decrease. So if you get an increase in pressure, then you need to shift the. It's a simple trick, but so it's nothing but E is equal to it's adiabatic relation, right? So
Yes,
P
sir.
P T power gamma equal to constant, right? Believe is
Sir, actually power should be gamma by gamma minus.
so here or here. Is this correct?
So Pt by Pc is equal to, yeah, that's correct, sir.
Yeah. Okay. So maybe let's calculate it then. Uh, So we need a throat. Throat is nothing but PC times 2 by gamma. Chamber pressure is nothing but 36 atmosphere. 36 into 1, then 2 by 24. As 1.24 divided by 1.24. How much is the pressure you are getting? It should be less than 36 ATM. But how much is it? So I'm getting. Yes, yes, Mohammed.
2.03 megapascal I'm getting.
Or you can write it like 20 atmosphere or
Yes, sir.
20.3, depends on how you want to put it. Uh, so this is the pressure at the throat. And what else you need to know? You need to know area at the throat. So how do we find area at the throat? That is so we can use this relation. M dot is going to be rho t at and velocity at the throat, right? So we know the velocity at the throat. Velocity at the throat is nothing but speed of sound at the throat. So a t, which is nothing but square root of gamma or t at the throat. We all know the molecular weight of
So,
gases, which is given. Yeah, yeah, Akash.
so, so, like I have another way, so like VT, we can also write area ratio like VT rho T by VE by rho E, right? Like take like arranging the equations. Like,
Yeah, so we don't know VE yet, right?
so VE is like jet velocity, right? We can find it
Yeah,
through
we can
the,
find out. So actually, that is coming in the next. Actually, we need to find the exit Mach number at that time. Yeah, also you can find. There are a lot of ways. Yeah, you are telling we can find it using m dot is equal to. Uh, it's going to be what is going to be expansion ratio is equal to we don't know expansion ratio. Do we know? Yeah, it's going to be rho t vt by rho e ve. Is that what you are telling?
yes, sir.
So here we don't know jet velocity. We don't know expansion ratio, right? We can potentially find Vt, we can also find rho t, and how do we find exit density?
So exit density that PV like ideal gas equation.
For that you need to know pressure at the exit, so which we can take it as ambient pressure.
Yeah.
And you also need to know temperature at the exit.
These are we've already found the temperature at exit, right? Like,
We found the temperature at the throat.
okay, okay, sir. Okay, sir. My mistake. Then. So,
It's nothing but we found this throat temperature. So this is T T P T. Here only it's T T E and P E. So we found only these two. We also don't know expansion ratio. So using this, so we will use this in upcoming because we need to find expansion ratio also. Okay. So right
okay,
now we don't know more than one parameter in that equation. So we will stick to a simpler equation because we know the mass flow rate. So that is the only one way out. So we know how much propellant is burning here. So that is going to be same as mass flow rate here also, right? Mass flow rate at the throat. So we can write this to be equal to 400 kg per second. Okay, and velocity of the throat you can find it like this, or and this also you can find. How much are you getting the area of the throat? So this is one way. Or if you want to do a most advanced way, this is from basic mass conservation you are doing. If you want to do a most advanced way, what we already know is mass flow rate is nothing but PCAT by C star. C star is nothing but what is C star? It's square root of R T, I guess, or PC by capital gamma. First you find C star. because you know the chamber temperature, you know gammas, okay, and you know molecular weight also, you can find C star. So this you can find. Once you find C star, you put it in the equation. You know the chamber pressure, and you also know the mass flow rate. So this would be easier to do this. We can also do using this first principles, but we can. Yes, Mohammed, do you have any doubts?
Sir, there is a error in PC, sir. Actually, we calculated for 36 ATM combustion chamber, but
Okay,
in the given problem 35. 35.
I don't know. I
Sir,
got strict. Uh-huh.
sir for actually we are getting 1.97 megapascal.
Uh, so maybe again, I don't know, 1.97. It's
Yes, sir.
fine. We can stick with megapascal. No problem.
Okay.
So now it's easier to find C star. We can find C star now. How much is it? It's going to be R naught by molecular weight Tc divided by the gamma is there. What is gamma?
It's a root of gamma multiplication of 2 by gamma plus 1 over.
Okay. So you can simply put everything in a square root and you can remove this one. Anyway, fine. Yeah. So how much are you getting? So maybe let's just find, let's just do one step at a time. How much are you getting this capital gamma? It's 1.24 plus 1, 2, 3, so is this approach clear? So we know C star velocity, right? So based on C star, we will be finding, we can find the area of the throat. Once we know area of the throat, we can find other things like expansion ratio, exit, everything. Okay. How much are you getting this capital gamma?
0.656. 0.656, sir.
Is going to be 8.314 divided by molecular, just molecular by 23.3 kg per kilomole. So you need to divide by 1000, right? So 0.30 into 10 means TC. What is TC? 3670. Alright, 3670 divided by 0.656. Okay, how much are you getting? Sure, this is within the road. Please be careful.
Sir, I am getting 1744.
744.
Point double four. Sir.
Thank you. Um, yeah, so we found the C star, and now we know m dot. M dot is equal to PCAT by C star, right? Now we can write the code to be m dot C star by PC. Okay, so which is 400 kg per second, 1744.4 divided by, sorry, yeah, correct, 1744.4 divided by chamber pressure, which is 35 atmosphere. The area of throat.
Sir, 0.196 meters square.
We have area of the throat. Okay. Basically, we completed the first question. Now we need exit mark number. How do we find exit mark number? So couple of things now right now. If I want to draw, I know PT, TT, then area and mark number at the exit. We know everything till we also know m dot. We can everything till throat. We need to find what happens after. We will consider this ideal expansion. Okay. So PA is equal to PE, which is equal to 1 atmosphere. Basically, we know PE also. How do we
So,
find? Yeah, Akash, please go ahead.
okay, sir, nothing else.
Yeah, fine. You can tell. You can use the same isentropic relation, right? The isentropic throughout the nozzle. So I know till throat. Then I find what is at the exit, right? Isentropic expansion. So I told you it's going to be ideal expansion. Ideal expansion. We already wrote this equation. Where we wrote? We know that this equation PC by PT is equal to TT by TC power gamma minus 1. We know pressure. Based on that, we need to get the Mach number. For Mach number, we need to know the temperature of the exit. So to get the
So,
temperature of the exit, yeah.
so like there is this relation, right? PE by PA equal to 1.88 Mach number minus 1 raised to minus 0.64.
Oh, okay. That relation is a little bit different.
Okay.
It has nothing to do here. We told that it's isentropic expansion. For in order for the flow separation to happen, what should be my pressure difference is what that equation tells. It doesn't tell
Okay.
what is my exit Mach number. Okay,
Okay.
so it is if you look at the equation, it doesn't come from first principles, right? It has power 0.64 and all. How can a 0.64 come from there?
Yes.
Right, so anything which you derive from first principles, let's say conservation of mass, momentum and energy, uh, equation is actually experimentally observed, and based on that they empirically came up with that equation. That doesn't, it is also for flow separations. So it's the way you find out the equations. If you, okay. Basically, what I'm telling is it's going to be isentropic flow throughout. So we can use the same relation. We can write PC by P exit is equal to T exit by TC power, I believe it's gamma minus 1 by gamma. Alright. Okay. So before there was throat here and here, right? Now it's a exit from here to here, or you can even write it like P T by PE is equal to TT by TC. Both will give you same results. Let's use this to find the exit temperature. Okay, or you can use this also. Anyway, it's going to give you the same temperature. So T exit by Tc is going to be Pc by P exit. Okay, and then yeah, now you can write T chamber times P chamber. Okay, so 3670. How much? Give me a second. Which are you getting? Chamber is 35 atmospheres, I believe. 3 to 5. Exit is going to be 1 atmosphere. So
So, so the equation should be PE by PC, right? In raised to gamma by gamma minus 1.
Yes, sir.
okay. Telling it should be PE by PC. Let me see. 1 second. E, E by PC. Okay. Basically, if you have an inverse relation, then gamma minus 1 should be here. Okay. How much are you getting? So you can write T 30.24 divided by 0. Shouldn't it be opposite? Right, exit is 1 atmosphere, TC is 35 atmosphere. Yeah, you're right. How much are you getting? Anyone calculating?
Sir, actually, relation has to be changed in power P by PC, gamma minus 1 by gamma, right? Is it right?
Still there's a confusion. Okay, 0.24 by 1 point. So basically, to avoid confusion, what we will do is we will look to remember how this relation came. Basically, I also don't know. What is the relation for adiabatic expansion? P by T power gamma equal to constant, right?
Yes, sir.
Yes, sir.
P1.
Sir, we can calculate, we can derive this equation from P1 V1 comma equal
Hmm.
to P1 V2 gamma.
P1 V1 gamma is equal to P2. Then change it. We know that PV is equal to gamma. P is equal to gamma RT by P. So you can just substitute it here. So, so here it will be 1 1. Basically, gamma RT is constant for this process. Isn't this gets cancelled? By P1 power gamma into T equal to P2 by P2 power gamma. Okay, so then P1 power gamma is equal to P1 by P2 P, which will be P1 by P2. Change it T1 by T2. If you want to write in terms of, let's say P1 is P chamber and P2 is P exit, T chamber by T exit 1 power gamma.
Sir,
Is that
actually, V1 gamma by gamma minus 1 by gamma, right? T1 by T1 divided by T2, gamma minus 1 minus gamma divided by gamma, I think so.
okay?
Sir, we actually we make it denominator into numerator.
So, how do you want to change it? P1 by P2 is equal to T2 by T1 into gamma by 1 minus gamma, right? I actually do the
Yes, sir, yes, sir.
chamber by P exit, then you can write like T chamber by T exit. We need is T exit, so we can replace it at T chamber by T exit is equal to P chamber by P exit power. Just take the exponential to the other side. So it if I want to find the T exit chamber divided by PC by PE at gamma minus 1 by. This is fine, right? So basically we usually what we do. So okay, let's just generalize it. I wrote a lot of T1 by T2, right? Basically we want to get T2 state from the T1 state. So what we basically do is we will just flip it. So if I want T2 by P1, then I need to write T2 by T1. Any ratio can be written as can be written like this. So this is fine, right? Either you can
Yes,
write
sir.
1 to 2 or 2 to 1. So if it matches 1 and 1 matches, then it should be gamma by gamma minus 1. If it doesn't match, it's going to be gamma minus 1 by gamma. That's all. Just add exponent to t. Let's say if you want to use this expression, then it's going to be P exit by P chamber is equal to T exit by T chamber power 1. So you can write it like P chamber power T exit by T chamber. So what you want is T exit. T exit is nothing but T chamber times PE by PC whole power gamma minus 1 by. So here let's use this then. This is clear, right, everyone? I think everyone is on the same page. P670 is going to be 1 atmosphere divided by 35, which is chamber pressure, power gamma minus 1, which is 2.4 divided by 1.2. Which are you getting?
Sir, 1844.22
1844.22
Kelvin.
velocity root of gamma RT. We still don't know what is the velocity at the exit. Velocity at the exit is nothing but jet velocity, right? It is going to be 2 gamma by gamma minus PC by PE. So if you substitute, what is the jet velocity you are getting? Yeah, T naught is going to be TC. Or you can please let me know your answers. Which is P3.3, I guess. P 1 atmosphere, PC 35 atmosphere. much is this? Or there is a more intelligent solution. Or you need to the total, I mean total temperature you can use, which is nothing but T by T exit is nothing but exit. So replace it like how Tc by T exit, because we know temperature minus. This is true for any compressible flow, isotropic flow. Okay, exit. This will directly give you Mach number. Here you will find the velocity and then velocity. What's wrong with that? Where is it? 34?
Sir, 2.6
2.6 kilometers per second.
0 kilometer per second.
2.60 kilometers per second. All right. So let's put it. Let's find the Mach number. Mach number 0.6 into 10 power 3 T, which is 3670, which is the Mach number. Sorry, this is not 3670. It is the exit temperature 1844. The exit, right? How much are you getting Mach number?
Sir, 2.87.
Okay, 2.878. Okay. We got the exit Mach number. In addition, we also found the jet velocity. So let's take this. Now we need to find the expansion ratio. That can be easily found, right? Because we know the area of the throat. We know the expansion ratio formula. What is the expansion ratio formula? There are a lot. We have the formula here. It will be easy. Gamma minus 1 times PC minus PE by PC. So you need to know there is a difference in ratio in denominator and numerator. Yeah, this is the formula. The expansion ratio you guys are getting. And I will substitute everything. Is going to be 35 atmospheres. And, the expansion ratio you're getting.
So expansion ratio 5.10. The numerator we are getting 10.96. Okay.
Thank you. So we are getting expansion ratio of 5 point. Once you found the expansion ratio, so the third question is done. All right. Now we are asked to find ideal thrust coefficient. So what do we know about ideal thrust coefficient? Which means that there's not going to be any um, exit because there's not going to be any pressure thrust, or the uh, exit pressure is going to be same as the ambient pressure, right? Real thrust coefficient, which is CF, we denote it as naught, which also has a these formulas. If you then it would be very easy to use the calculator to find a lot of things here, right? What are you guys getting? Thrust coefficient is just mere substitution of each and every value. So I will just substitute everything. E by PC, which is 1 by 35. Are you guys getting? Zero point 0.487.
Yes, sir, correct.
Okay.
Yes, sir, I am getting.
Thank you. Um, then, what is the next question has been asked? So this is the ideal thrust coefficient. That's fine. If the calculate the actual thrust coefficient, if the rocket is operating at the altitude of 16 kilometers. So now the rocket is at 16 kilometer. Uh, so this coefficient is what they are asking, and for the we don't have any pressure thrust coming in. So here we have the ambient pressure to be 0.01 megapascal. So we will include that. So how does the formula now look like? The actual thrust coefficient is going to be CF is nothing but CF naught, or this big equation, right? Plus PE by PC minus PA by PC divided by AE by AT. What we know about AE by AT? AE by AT is nothing but expansion ratio epsilon. This is PE minus PC. Let me write it down. Plus this PE. Did we found PE? Okay. I think we didn't find PE.
The equal to atmosphere.
Okay. Right, right, right. P is equal to atmosphere because it is designed for, yeah, yeah. So mono much are you getting? How much is there? It will also be around 1.
Sir, 1.618.
This is the CF we have, and then we are asked to find the, this is done, so we are asked to find the specific impulse at sea level. We already know what is specific impulse. Specific impulse is nothing but we know about specific impulse. Specific impulse is nothing but CF times C star, right? We found C star, which is beneficial right now. What will be CF at sea level? CF at sea level is going to be CF naught, right? Because it is designed at that condition, right? Is it coming? CF naught is 1.487. C star, what is C star? 744.44. Are you getting?
2593.98.
So you can notice one thing here. We already found the jet velocity, which is also 2.59, maybe 2.59. You might have 6, right? 9 kilometer per second. So actually, at this condition, we can write ISP to be VJ. Okay. So you can either just use the VJ or you can multiply. You will end up getting the same results. All right. So this is ISP at the sea level. Now there are few interesting questions. I don't know how much I can cover within 8, 9. Okay. Just cover only 4 questions. I think it's pretty easy. So if this semi-divergence angle is 15 degrees, okay, calculate the divergence loss coefficient, for which we already know the know the relation, right? What is the um divergence loss coefficient relation? Are you guys able to recall? It has something to do with cos alpha. Cos alpha by 2. We know semi-divergence angle is 15 degrees. So if you substitute it, 1 plus cos. The question was, what is the uh, loss in thrust? Which again you know the formula, which is nothing but 1 minus lambda. What is the divergence coefficient you are getting? The exit area of the nozzle, which again you know is easy. You know expansion ratio, which is EAE by AT. Now you can find of the divergent portion. We can so this is also, I think you guys should know, it's nothing but alpha here. And then the This is the central line, right? So there is this convergent portion, there is this divergent portion. Similarly here, here, and we know this is the R at throat, radius at the throat, and this is radius at the exit, which we know, right? It's a conical nozzle again. So we need to find this length of the divergence LD. I think you can find it. So you can write this problem as a triangle where this is going to be RE minus RT, and this is alpha, this is LD. So what we know is we know tan alpha. Tan alpha is nothing but opposite side by adjacent, right? Divided by adjacent. What we need to find is the LD, which is RE minus RT divided by tan alpha. You can write LD to be RE minus RT times. In this way, you can find the length of the nozzle also. So it actually crossed 9 o'clock. Maybe I will stop here. Please complete these uh, remaining 4 questions, which divergence loss coefficient, thrust loss, and then exit area of the nozzle, length of the divergent portion also. All right. If you have any questions, you can stay back and ask. I will stop here. Okay.